in the first lab, one of the requirements is to use 7-segment display to show the seconds remaining when the time counter counting down for switching the light colors. So for the 7 segments, it's quite simple. This little component has been available for a long time, and because you can see from the design that it has 7 segments that you can lit up individually, and that's why it's named as 7-segment displays. And you have an option of using individual ones, and also in the lab development kit, it has a 4-digit 7-segment, so which has little controller in it to bundle up all the pins. And each of these individual segments can be lit up individually. You can use this table to decide how you light up the displays segments to come up with different numbers. And because the controller itself already programmed so that you only need to follow these patterns to lit up individual digits on the 7-segment display. There's a minor difference on the properties of the 7-segment. Depends on its common cathode or its common anode. So the polarity of these pins could be the opposite. And this table shows the common cathode. And if you're using a different one, then this is all going to be reversed. So that's basically how we lit up the individual display by setting these 8 bits for the 8 input pins on this 7-segment display.
Excuse me, Professor?
Yes.
Am I reading it wrong? To display 1, is it saying to show B, C, and G? That doesn't seem to make much sense to me. I don't know if I'm misunderstanding the chart.
Okay, so B, C, and G. B, C, display 1, B, C, and G, yes. Let me try to 0. So A, B, C, D, E, F. Yeah, I think this should be a 0. Okay, now when you connect this to a microcontroller like Arduino, you have options to connect every single pin from the 7-segment directly to Arduino. But then you're going to be using a lot of the pins from Arduino, which can become scarce if you have other components you need to connect the microcontroller to. So a common design is to use a shift register. And that's the purpose of this 74HC595. This is an IC, and that's included in the kit. And the purpose of this IC is to use fewer number of pins to the microcontroller and to generate these necessary 8 signals for driving this 7-segment. So this is the 7-segment. You have A through DP and G1, G2, which are commonly connected to ground to enable that. And you can see that the 7HC595, which has 8 output, because this is an 8-bit shift register. The output of the register is 8-bit, and the input is 1 bit. And we see Q0, Q1 up to Q7. These 7 output from the shift register will be used to drive the 8-bit input to the 7-segment display. Okay. And on the input side, we will connect this DS and the store clock pulse and shift clock pulse to the Arduino Mega microcontroller. I will talk about this 7-segment shortly, but here we can see that using this shift register, we effectively reduce the number of pins required for driving the 8 inputs to the 7-segment to now 3. So that's the benefit. And also this shift register can be, driven and separately on the shift clock and the storage, which is the output clock. So you can update the value at some point and decide when you want to refresh the display to output the 8 value onto this 8 inputs to the 7-segment display. Okay. This is the picture that you might refer to when you connect the 7-segment. Although this is only 1 digit, we have another document that shows the 4-digit 7-segment display. So let me switch to that one. So this is the lesson on the 4-digit 7-segment display. You should be able to access all these documents when you download the resource zip file from the EECLU website. This is 4-digit 7-segment. It's based on the 1 digit, but internally it has some circuitry to drive the, basically bundle these 4 digits together and drive them together. The wiring to these 4-digit 7-segment is a little bit different from the previous example. Although the principle is the same, we use this shift register down here to reduce the number of pins required on the microcontroller. So this is the shift register. The model number is 74HC595. So it's 8-bit serial in and serial or parallel out shift register with output latches. And it's a tri-state, 3-state. So let me explain a little bit what this IC does and some of the interesting design that we can leverage. First of all, this is a shift register. The concept of the shift register is that you will have some one serial bit going into this IC. It's going to shift into this IC. Internally, it will be stored in a register. And the output from this IC is 8-bit. So that's why we call it 8-bit parallel output. You can also do serial output through 1 bit. So it's possible that the most significant bit you shift in, the most significant of the register can be shipped out of the register, and such that it will be cascaded into the next level or next shift register. So you can chain a few of these if you have that specific needs or requirement. Internally, there's a storage register which stores the current value in the register. And we can, of course, output the 8-bit altogether at the same time. And that's actually what we need to drive the 7-segment. But also you can choose to output a high impedance. That's why it's called a 3-state or tri-state in some cases. Tri-state is an important concept. Tri-state means that you can have a output as 0 or 1 or a high impedance. High impedance is very useful, especially when you have multiple of components connected to the same wire. We call it a bus. With this high impedance state, you basically isolate the IC from that wire, from that output wire, such that you, if you don't want this output to affect other outputs, from other components, you can do that. Otherwise, the value that you output on this wire from this IC will be always there available or having impact to other ICs. And when you have multiple of these connecting to the same wire, you will see a lot of interference, and that's not what we want to see. You don't have to always use tri-state or high impedance output, but in some cases you will need that. So what we have here is this serial input. So we have 1-bit input, and the data, the input is shifted on the positive going transition of this SHCP input. You can think about this as a shift clock. If you have a rising edge on this clock, then the value that you put on the input, which is, maybe I'll show you the next one for this. So this is the one you have in your lab kit. It has 16 pins, 1 VCC, 1 ground. So you essentially have 14 useful pins left. And you have Q0, Q1 up to Q7. So you have 8 output, pins. So you can output an 8-bit value from this IC. And you have DS, that's the input serial input. And you have output enable, which is the one you can use to say, output either a 0 or 1, or if you put a logic 1 here, the output will be in a tri-state mode, so it will be high impedance. This SHCP is what I just explained. This is the shift clock pulse. So if you have a change from 0 to 1 on this pin, then the value from this DS will be shifted into this register. And if you have a ST clock pulse, so that's the storage clock pulse that will be used to update the output of the register. You can also choose to shift 1 bit out, and that's the Q7 prime here. This is the basically the most significant bit that we shift outside the register. And in your lab 1, you don't need to use this pin at all. Yeah, so this is the table. And so we have data parallel output. We have series data output for cascading to another shifted register. We have a master reset to clear the content. We have the shift register clock input and storage clock register clock input. And DS is the serial data input. Okay. So what you do in this first lab is, let me switch back to, maybe I can share the whole screen. So coming back to the design that you have here for driving this 4-digit 7-segment, you will connect the 7-segment, the inputs to this shift register, so that the output, the 8-bit parallel output from the shift register will be driving this 7-segment, 4-digit 7-segment. And then we're going to be using this D10, D9, D8, these 3 pins from Arduino to control this shift register. So with these 3 wires, we can put these zeros and ones through this serial input to the shift register. And the purpose is to update a value on this output so that we can put a number here on these 7 segments. So this is basically how this 7-segment works with a shift register and the microcontroller. I encourage you to start just trying this lesson. This is lesson 5. And you can just go ahead and implement the same connection. And in the resource CD or the zip file, you can find the source code for this design. And you can try to display different numbers on this 4-digit 7-segment. And use this as a start. Then you can design your state machine so every second you'll be updating this number. And so you'll display the remaining seconds on this 7-segment display.